section that we're doing today is about the dot product. So we've talked about adding and subtracting vectors, so now we're going to talk about multiplying vectors. There are two ways to multiply vectors. The first one is the dot product that we're learning today, and the next one is the cross product, which is the next section. So let's say that if you have vector A, which is, let's make it a three space, A1, A2, A3. I always leave that comma off on accident. And B, vector B to be B1, B2, B3. Then the dot product of A and B, vectors A and B. Make sure you have your vector notation. It's important that it's a difference between a vector, a scalar, and a component, so be sure that you do that. And the notation is vector A dot vector B. You have to write the dot in and make sure it's visible. So what we do is we multiply them component-wise. So we're going to take and multiply A1 times B1 is the first one, and then we're going to add A2 times B2, and then we're going to multiply add A3 times B3. So A dot B, vector A dot vector B is A1 B1 plus A2 B2 plus A3 B3. Now notice that's going to give you a scalar. When you do this, it gives you a scalar. So sometimes it's called a scalar product or an inner product, but most often we call it the dot product. So it's very similar if it's if A, let's say if A equals A1, A2, and B is vector B, vector notation, gracious, and B is B1, B2, then A dot B is vector A dot vector B is A1, B1 plus A2, B2. So a lot of what we do, we go ahead and write it in three space because that's where we're going to use it the most, but it works in two space as well. So this gives you your dot product. It's very easy to see. Let's leave it on the screen and look at an example. So let's do, let's let vector A equal -1, 7, 4, and vector B be 6, 2, 3. Then A dot B, vector A, my screen wants to move instead of writing, dot vector B equals, now you take -1 times 6, and we're just going to write -6, plus 7 times 2 is 14, plus 4 times 3 is 12. So that gives us 20. As you can see, this is a scalar, and we'll be doing a lot with these scalars and talking about these scalars. They can tell us things about vectors. Let's do another example. Let's use the IJK notation. So let's say we have I, vector I minus 2j plus 3k. I was going to copy one, but I messed up. And let's go ahead and say dot, and let's skip the vector notation to define it. And let's say 2j minus k. So again, we're going to go component-wise. So the numbers in front of I is just 1 because there's no I in the next one. Plus -2 times +2, the coefficients of j would give us -4. So let's kill the plus there. And then we have, we should probably do it correctly. Let's erase it and write it in. So -2 times +2 is -4. We could have used parentheses, I guess. And then for k, we have the coefficients of 3 and -1, so they multiply to make -3. So this one has a dot product of -6. So the dot product is pretty easy to find. It's helpful in lots of ways. That's what this whole section is about. And so let's look at where we're going with these. Before we do, let's talk about the properties of dot products. So these are the properties of the dot product. So if A and B and C are vectors in V3. Now notice here they don't have vector notation because it's bold. In a textbook, a bold means a vector, and a, a non-bold italics means a scalar. So that's what we have happening here. It's usually defined since since we can't write in bold, we need to write vector notation. So let's also talk about this V3. V3 is the set of all vectors from 3 space. So these are vectors with 3 components. So that's what V3 is. It's the set of all vectors in R3. Okay, so let's look at number 1. Before we do, let's remember that the length of A equals the square root of A1 squared plus A2 squared. And we're in V3, so we have A3 squared. All right, so there are 2 ways to prove these mathematically. The first way is you work on one side, make it match the other. The second way is you work both sides separately to see if they match. Let's start with the right side. So let's take A dot A. Remember, we're in 3 space. So we have A1 times A1 plus A2 times A2 plus A3 times A3. Remember the A is A1, A2, A3. So when we do that dot product, they look like this. So we're going to say this equals A1 squared plus A2 squared plus A3 squared. Now reading the future, I know if I put a square root over that, it equals the length of A. So let's call it the square root of A1 squared plus A2 squared plus A3 squared, and square both sides, square that completely. Then we could call this parentheses the length of A, close parentheses, squared, which we can call the length of A squared. Now, most of you as students would do this part on the right-hand side and then work out the left-hand side to match. And that's a beautiful way to do a proof. Okay, number 2 says the commutative property. The commutative property says we can change the order that we add or multiply in real numbers. So 2 times 3 equals 3 times 2. So here we're saying the dot product, A dot B, and it equals B dot A. But let's write it out. So this would be A1, A2, A3 dot B1, B2, B3. So let's do the dot product and multiply those, and we get A1, B1 plus A2, B2 plus A3, B3. Now what we really want to do is switch those, but remember that all of those components, A1, B1, A2, A1, A2, B2, all of those things are real numbers. So A1, B1 in real numbers is the same thing as B1, A1. So we can use the commutative property on the components because they are numbers in R3, which means all of them are real numbers. So we're going to switch them so that we're going to use the commutative property to say the B's come first. So we're going to write it as B1A1 plus B2A2 plus B3A3. Now we're going to pull that back apart and say this is B1, B2, B3, dot product, A1, A2, A3. So this is vector B dot vector A. The commutative property does hold. Now, here's the good news. We're going to look at the rest and not prove them, but you needed to have seen something like that. If you take a linear algebra class, you'll probably have to prove them. Some Calc 3 classes make you prove them. We're not going to do that, but it is helpful to see that you can. It's not beyond your reach or understanding. Number 3 says A dot, the sum of B plus C equals A dot B plus A dot C. So this means the distributive property holds. The distributive property of multiplication. And then number 4, we have the associative property of a scalar. Now notice it's the associative property of a scalar. So we have a scalar times A dot B, or a scalar times the dot product of A and B, or A dot the scalar of C times B. So that works. And then number 5, you have the 0 factor times A. That means that 0, 0, 0 dot A equals the number 0, the scalar 0. Notice that in number the left one is bold because it's a vector, and the one on the right side, the equal, is not bold because it is a scalar. So these properties come in handy that you can use them. You don't need to memorize them. It may make your life a little bit easier, but it's not too bad. So we have a theorem. By the way, in math, theorems are things that are proven. So you could prove it. This theorem says if theta is the angle between vectors A and B, then A dot B equals the length of A times the length of B. Now notice those are both scalars, so it's not a dot product, it's just multiplication times cosine of theta. Now, physicists use this as their definition of dot product and use it. It's easy to prove using your law of cosines. So think about the fact that, I don't know why I'm drawing it on here, but I'm going to, so here we go. So let's say we have vector A here, vector A and vector B. Then this vector here is, I missed it, but this vector here is A minus B. And this theta is the angle between them. So that's what the theta is. That's the angle between the two vectors. And as I said, it's not a hard proof using the law of cosines, but you don't have to do it. So let's consider for a moment a corollary. A corollary means it comes from the other one. It comes from the theorem. It can be proven, but it's not quite as strong. So it says if theta is the angle between non-zero vectors, if theta is the angle between non-zero vectors A and B. Now it's important in this case it's non-zero, but we didn't do that before, between non-zero vectors, because it could be zero before, between non-zero vectors A and B. Then we're going to solve the above theorem for cosine of theta. So if you look at it, cosine of theta equals A dot B over the length of A, the length of B. So now you can see why they have to be non-zero vectors, because you're dividing by the length of them. So that's why in this corollary it gets stated. Now, in my opinion, you need to learn one of the two. I would learn this one because you can easily do the math to get to the corollary statement. So if you're given A and B, you could find cosine of theta, and that's what we do with it a lot. So we're going to pick up this theorem. In fact, I'm going to slide my screen up, and we're going to use this corollary right here. And let's say that the problem says, the example, there was another example, but it was dumb, so we're going to skip it. It says find the angle. It was just plugging things in. Okay, find the angle between vectors A and B. Between A equals the vector 2, 2, negative 1, and vector B equals 5, negative 3, 2. Vector notation is important. Make it a habit to write it every time because you need it to indicate it's a vector, and good math habits make good math students. So if you leave it off, you're likely to leave it off when you're taking a test, and then you're not saying a vector and everything has changed. So be careful about that. Now, in order to find the angle between, we're going to use this formula that we looked at up here. So we're going to use a dot product and the lengths. So let's start with A dot B. A dot B is nice and simple. 2 times 5 is 10. 2 times negative 3 is negative 6. And negative 1 times 2 is negative 2. So 10 minus 6 is 4, minus 2 is 2. So our dot product is 2. Now we need the length of A and we need the length of B. So let's start with the length of A. 2 squared is 4, plus 2 squared is 4, plus 1. So we get the square root of 9, which is 3. Nice. And the length of B is 25 plus 9 plus 4, which makes the square root of 38. Interesting. So then we have cosine of theta equals A dot B, which we found to be 2, over 3 times the square root of 38, which is all well and beautiful. So then we can do inverse cosine of 2 over the square root of 38. Do I need to write that for you? So theta equals, you don't need to write this down when you're doing the math for me. You've been doing this since trig. You should be fine. So theta equals 84 degrees. Most of the time, using your calculator, most of the time we're doing Calc 3 in degrees, not in radians. If you did radians, you get 1.46. So WebAssign almost always calls for radians. So keep that in mind. Now, something I want you to think about is let's pretend, let's say, example, what if our cosine of theta equals 0? Then what does theta equal? Hopefully you said 90 degrees or pi over 2, which is true. That's where it happens. So we have an important corollary that says that two vectors, it's a corollary, a theorem, a statement, and it's probably a corollary. It's not labeled, it's just in a box. So let's make it a note. There we go. Let's call it a note. Note two vectors, A and B, are orthogonal. That's an interesting term. I don't know that you've ever seen it before. We use it a lot in higher mathematics. Are orthogonal if and only if. By the way, if and only if is abbreviated IFF in higher mathematics. If and only if A dot B equals 0. So there's a couple things I want to tell you here. First of all, the word orthogonal also means perpendicular, but it's very specific. It's orthogonal means perpendicular vectors. And the if and only if is important because it means that, remember, an if then reads only to the right. If this, then this. So an if and only if reads both ways. It says if this, then this, and reading backwards, if the right side, then the left side. So when you go back and read it the first way, the if and only if this way, it says if two vectors are orthogonal, then A dot B is 0. And when we read it the back way, if A dot B equals 0, then two vectors are orthogonal. So because cosine of 0 equals 90 degrees, two vectors are orthogonal or perpendicular if A dot B is 0. So that helps us to determine if two vectors are perpendicular or not. So let's look at that. So example, let's say is 2i plus 2j minus k perpendicular or orthogonal to, they use them interchangeably, which is crazy. They should just use orthogonal. 5i minus 4j plus 2k. So how do we determine if they're orthogonal or perpendicular? You look at the dot product. So let's say A dot B, because I'm too lazy to write them again. And then the component, the coefficients of I, or the components of I, 2 times 5 is 10, plus the j's make negative 8, and the k's are negative 2, so that equals 0. Therefore, vector A is perpendicular to vector B. Nice. Now, this is not anything you need to memorize. It's just interesting information. But if your dot product is greater than 0, then you have an acute angle. If it equals 0, you have a right angle. And if your dot product is less than 0, you have an obtuse angle. It's an interesting conversation. It's interesting. One thing they don't get into here is parallel, but they expect you to figure it out in some way. So let's talk about parallel for a minute. Let's make a note. And let's make it similar to the perpendicular note. The textbook doesn't really do it anywhere, but we will. Two vectors, A and B, are parallel if they're scalar multiples of one another. Think about parallel lines. If you take one line and multiply it by any constant, then and you get another line, then they're parallel. So for an example, let's let A equal 2, 3. Then a parallel B would be, let's multiply by 2 to get 4, 6. A parallel C could be negative 2, negative 3. A parallel D could be -20, -30. So as long as you multiply, if one of a scalar multiple of the other, then they are parallel. And it doesn't have to be a whole number. You could multiply by a fraction. Let's multiply by half so we get 1 and 3/2. So parallel vectors are easy and fun to do. There's some problems in your homework, and let's do one of those real quick. Let me find it real quick. Okay, so this is not the one from your homework, but it's similar to your homework. It's actually number 24. Your homework is number 23. So the directions say determine if the given vectors are orthogonal, parallel, or neither. So determine if they're orthogonal, parallel, or neither. Now, I like to start with parallel because obviously one is a multiple of the other. So let's look at number A. You got a -5 and a 3 and a 4 and a 4. They are not multiples of each other. So let's do, for letter A, let's check orthogonal. So let's do U dot V equals -5 times 3 is 15, plus 4 times 4 is 16, and then -2 times -1 is +2. So we got 13. Therefore, this is neither, because they're not multiples of each other, nor is their dot product 0. Letter B. Let's look at U dot V. So 9 times -6 is -54, plus -6 times 4 is -24, plus -3 times 2 is -6. I automatically write my plus, and I didn't want to go back and erase them, that's why. So this is definitely not 0, but I can't leave it hanging out like that. So let's go ahead and finish it. -30, -84. Now, are they multiples of each other? They might be. So if we take 9/6, the coefficients of I negative, I have -3/2. Now, since I took the 9 first, I'm going to take -6 and multiply it by -3/2. And I do get +9. If I take 4 and multiply it by -3/2, we get -6. And if we take -2 and multiply it by -3/2, we get +3. So you can see those are the coefficients for U, therefore they are parallel. And then the last one, letter C, they're not parallel. There's no way. I say that sometimes it's obvious to some people and not others. But if you take this first component, you multiply by 1. The second component, you need to multiply by 0. And the third component, you would need to multiply by -1. So it can't be parallel because you're not multiplying by the same thing all the way through. So let's check out the dot product. We have U dot V equals C times C is C squared, plus C times 0 is 0, plus C times -C makes -C squared, which equals 0. Therefore, they are perpendicular. Let's not write perpendicular. Let's write orthogonal, like good mathematicians. So A is orthogonal to B. I'm sorry, U is orthogonal to V. And let's continue on. This part is about direction angles and direction cosines. So a direction angle is the angle that a non-zero vector A makes with each of the axes. So vector A and the x-axis make this angle alpha, which is kind of hard to see in this picture. It's a little easier to see the beta. You can see the angle between the y-axis and vector A, and gamma, the angle between the z-axis and vector A. And then we also have the alpha that we talked about. So the direction angles are the angles alpha, beta, and gamma. Let's write that down. The direction angles between vector A, well, we didn't need to write vector, but that's okay, between vector A and each axis. So the x-axis, we use alpha. The y-axis, we use beta. And the z-axis, we use gamma. Gamma is probably a little more curvy like that, but it gets a little sloppy and it looks a little different every time because we're not a typewriter. So it works out. Now the cosine of these direction angles is really important. So these are the direction cosines. Remember that when you write cosine, if you just write COS, you always need an angle to go with it. So if we take the definition of cosine of theta that we used before, it says A dot B over the length of A, the length of B. And if we take it in respect to each axis, so when we look at the x-axis, we're looking at just the first component here. So let's go ahead and split it and say cosine of alpha equals A dot I over the length of A times the length of I. Now remember, A dot I gives us A1 times 1 plus 0 for x, y plus 0 for z. And then here we have the length of A. And since I is 1, 0, 0, the length of I is just 1. So what we end up with is A1 over the length of A. Now you're not going to write all that every time. We're going to go ahead and cut that down to say that cosine of alpha equals A1 over the length of A. Similarly, cosine of beta is the second component because J has a 1 in the middle. So we're going to say A sub 2 over the length of A. And lastly, we're going to say cosine of gamma equals A sub 3 over the length of A. So these are your directional cosines. They give you the angle between the axis in question and the vector that you have. Really, truly, these values are the components of the unit vector in the direction of A. So you would see that to be true. But I think the homework explains it well because you're going to find the cosine, you're going to find the direction cosines, which are these values, and you're going to find the direction angles and find alpha, beta, and gamma by using inverse cosine. So let's look at one of these problems. In the exercises, it says, I think they state it better, so let's do that. I'm going to call it an example, but it's actually number 34 in your book. It says -6 to 9. And the directions say find the direction cosines and the direction angles of the vector. Find the direction cosines and the direction angles of the vector. They give very definite directions in WebAssign, and in the book it says give the direction angles correct to the nearest tenth of a degree. So they tell you right there that you're in degrees. So we're going to say that first of all, we have A1, A2, A3, so we need the length of A. I'm going to come up here and say the length of A equals the square root of -6 squared makes 36 plus 4 plus 81, and 40 plus 81 is 121, and the square root of 121 is 11. By the way, if one of your if one of your numbers ends up to be an improper fraction, you messed up because it's a unit circle of 1. The first time I did this problem, I accidentally wrote 18, so I couldn't get all the numbers. So keep that in mind. If that happens, you probably made a mistake. All right, we're going to say that cosine of alpha equals, and we'll take our first component, -6 over 11. And our second one is cosine of beta, so it's the second component, which is 2 over 11. And our third one is cosine of gamma, which equals 9 over 11. Now, these are your direction cosines. So I like the answers better that way. But in WebAssign, they're going to say part A is -6 over 11, 2 over 11, 9 over 11. By the way, if you were to write in brackets your vector notation, this is your unit vector. So that's an interesting note to make, that your cosine of each angle is equal to that component's unit vector piece. So that's kind of cool. Okay, so now let's talk about, those are the direction cosines. We've got that. Now let's do the direction angles. So you're going to use your calculator to find the direction angles using inverse cosine because we don't do this in our head. So don't use the negative. Remember that you're technically working between the x-axis and some vector here. So it's an acute angle, so it's a very small angle, or it's here. So either way, you're in a right triangle and it's an acute angle. So just do the sign. I mean, don't do the sign, just do the positive. Then alpha will be inverse cosine of 6 over 11, which is 56.9 degrees. Beta is inverse cosine of 2 over 11, and that gives us 79.5 degrees. By the way, I like 1 decimal point. When in doubt, 1 decimal point. And then gamma is inverse cosine of 9 over 11, and that's 35.1 degrees. So there you have your directional cosines and your directional angles, the direction cosines and the direction angles. So I hope that part makes sense. All right. In this picture, you can see projections. So the projection, the scalar projection of B onto A is the shadow that you can see right here. So you can see the shadow, and that's called, this is the notation, the projection of B onto A. If you look at the second figure, if B is there, then this is still the projection of B onto A. So that's what it looks like. Now what we have down here is called the component of B onto A, and it's the scalar projection. These are the vector projections. This is what you really have right here. These top two are your vector projections. And the bottom one is the scalar projection. What it is it's the signed magnitude, so it's the plus or minus magnitude of that point of the projection. So we have some formulas here. Let's start with the scalar projection. The scalar projection of B onto A is written as the component of B onto A. And the formula is A dot B, vectors, so A dot B over the length of A. And as you can see, we're going to have a scalar over a scalar. So it's called the scalar projection. Now, this is the signed component. This is the signed magnitude of the vector projection. Okay, so this is your scalar projection. This is the first part. And then let's talk about the vector projection. Vector projection is the formula is the projection of B onto A. I think this notation's weird, so if you do, I'm in it with you. Now what we're going to do is we're going to take the scalar projection we have above and not redo it, because generally we start with the scalar projection and then we're going to multiply it by A over, we're not going to put a dot there, vector A over the length of A. So what we have is we have a vector that is the shadow of B. So note, this is the shadow, kind of B onto A. So it's a vector answer. And let's say here we have vector B, and here we have vector A. Then here we have the shadow or the vector projection. So this is the vector projection, the projection of B onto A. So let's look at an example. So this example says find the scalar projection and the vector projection of B, vector B, 1, 1, 2, and vector A, negative 2, 3, 1. So let's start with the scalar projection, which is the component of B onto A. And remember that formula is A dot B over the length of A. So A dot B is negative 2 times 1 is negative 2, plus 3 times 1, plus 2 times 1, over the square root of A. A is the second one here, so negative 2 squared is 4, plus 3 squared is 9, plus 1 squared is 1. If I don't write out all my steps, I tend to mess things up and lose them. So negative 2 plus 3 plus 2 is 3. And on the bottom, we have the square root of 14. Rationalizing the denominator is kind of a thing of the past. This is your scalar projection here. So this is your first answer. And then we're going to find the vector projection of B onto A. And we're going to take that answer because remember, it's the formula is A dot B. If you write the formula every time you use it, it will help you learn it over A. So that's my scalar projection that we already found times the vector A over the length of A. So we have the vector A over the length of A. Now we could do this differently, but let's not. So the scalar projection is 3 over the square root of 14. And then we have vector A, which is negative 2, 3, 1 over the square root of 14. So this means the projection of B onto A is negative 2. We're going to distribute that 3. And then we have the square root of 14 times the square root of 14 is 14. So we have negative 6 over 14, which reduces to negative 3 over 7. And then the next one, we have 9 over the square root of 14. And the last one, we have 1 over the square root of 14. So that's our projection of B onto A. There are two strong applications here. Well, there's one strong application here. It's the application of work. And one of the projections that we use in calculus, in physics, is to calculate work. And you can see, according to the figure, that here is the displacement. D stands for displacement, catch that, the displacement vector. And F is the force vector. So when you look at the projection of the force onto the displacement, that's the work that's done. So this is the formula we're going to use for work. So the work done by a constant force, F, is the dot product F dot D, where D is the displacement vector. So there's lots of things happening here. There's a formula here where work equals the length of F times the cosine of theta times the length of the displacement. And all we did right in this middle part is rearrange it. But if you look back at your definition of dot product, the dot product can also be force times displacement equals length of the force times the displacement times cosine of theta. So before we used we used A dot B equals the length of A times the length of B times cosine of theta. So that's the same thing we have here, the force times the displacement, which equals work. So let's look at an example of one of those. So this problem says find the work done by a force. So let's remember that work equals the length of the force times the length of the displacement times cosine of theta, or the force dot product with the displacement. So F dot product D. So the work done by a force, so here's our force vector right here, that moves an object from this point along a straight line to this point. The distance is measured in meters and the force is in newtons. So remember, meters and newtons becomes joules when you work in force. So you either have meters, newtons, which becomes joules, or you have foot-pounds. In order to find the dot product of F and D, we need to, first of all, find the displacement. So we have two vectors. We're starting at 0, 10, 8. I'm sorry, we have 2 points, 0, 10, 8, and 6, 12, 20. And we need the displacement vector between the two. So we're going to make the head 0, 10, 8, and the ending point, the tail, 6, 12, 20. So 6 minus 0 is 6, and 12 minus 10 is 2, and 20 minus 8 is 12. So that's our displacement. And we know that F, well, it's an IJK format, but I started with vector format. So let me switch this one to 8, negative 6, 9. Now we learned that the dot product is commutative, but let's go ahead and find F dot D according to the definition of work. So 8 times 6 is 48, plus negative 6 times 12 is negative 12, plus 9 times 12 is 108. So when we add these things, we get 144 joules. That's the amount of work done. Let's look at one more example, and then we have one more problem that I think will be helpful. A wagon is pulled a distance of 100 meters along a horizontal path by a constant force of 70 newtons. So here we have a force. The handle of the wagon is held at an angle of 35 degrees above the horizontal. Find the work done by the force. So let's go back to our work formula. So work equals the length of the force times the length of the distance times cosine of theta. So it could be it could be the dot product of the force and the distance, but we don't have those. So if you look at it, the magnitude of the force, that's what we usually call it the length, but it's the magnitude. The magnitude of the force is 70 newtons, and the magnitude of the displacement is 100 meters. Do you see Newton meters right there? So Newton meters, and then the handle of the wagon is at an angle of 35 degrees, so theta is 35 degrees. So then we're going to say the work equals the magnitude of the force is 70 times 100 times cosine of 35. And when we plug that into our handy dandy calculator, a TI-84, as my friend Courtney would say, is the amazing calculator, we have 5734.06 joules, because this is Newton meters. If it was foot pounds, your label would be foot pounds. But I think you've already had some physics, so you would know that if you have feet and pounds, it becomes foot pounds. And if you have newtons and meters, it becomes joules. So there's one more that I wanted to talk to you about. Let me pull that up real quick. This problem says use vectors to determine if the triangle with vertices P, Q, and R is right angled. So what you want to do is you want to create your vectors for the three triangles. Now I know this is three space, but it helps for me to think about a triangle. So you shouldn't draw a right triangle because then you're assuming it is somewhere. So let's pick P, Q, and R. So you would need the vector for PR, and then the vector for RQ, and then the vector for QP. Now, if any of these are perpendicular, then you have a right triangle. And if none of them are perpendicular, you do not have a right triangle. So I'm not going to work that out for you, but remember that to be perpendicular, the word is orthogonal. And how'd you get orthogonal? If A dot B equals 0, then they're orthogonal, which is perpendicular. So that should help you accomplish that problem. All right, have a great day, and I hope you enjoyed the lesson.